All right, welcome everybody to the lecture today. It's a pleasure to have Christian Theobalt here talking about his research. So Christian is a professor at the Max Planck Institute in Saarbrücken. He is leading the Graphics, Vision, and Video Lab. And I think it's fair to say Christian is one of the pioneers at the intersection of graphics and computer vision. And he has, of course, published many papers, but many of his works are also really well known in both communities, which is really exceptional. Even at an early career stage, his work was known famously. And I can also say from a personal experience, Christian has also been one of my mentors. I had the honor to work with him very early on, and I can say both at a personal and academic level, he's really an inspiration to the community and every upcoming researcher. So I'm very happy to have him here today, and I'm really curious what cool research he's been doing.
So thank you very much, Matthias, for this very kind introduction. It's my great pleasure and honor to have the chance to present to you today some of the work we do at the intersection of graphics, vision, and a bit of machine learning. So, I mean, this is also a great pleasure for me because I have the chance to present here in Matthias' lab, and Matthias and me, as Matthias already mentioned, have been working on together for many years already. So I will talk to you today a little bit about some work we do in the area of reconstruction and neural rendering of real-world scenes, mostly talking also about things which were not exactly the projects that Matthias and we have been working on together, but some other things here. So let me start with a little introduction. So one of our long-term goals is essentially to generate new generations of methods for real-world reconstruction and synthesis, and that's best maybe explained with an example. So imagine you have a general real-world scene like this one here, where you have very complex motions and deformations. Essentially, everything is a priori unknown. You have occlusions, lighting is uncontrolled, and everything. So ultimately, in the very long term, what we would like to do is to essentially record such scenes with just very sparse sensor data, just with a single camera. And from these very sparse recordings at high efficiency, reconstruct detailed models of essential aspects of the scene, like the dense geometry of the scene at very high quality, the motion and deformation of the scene at high quality, but also other properties that could be of interest, like material, illumination properties, and so on. But ideally, we would not like only to reconstruct these scenes, but also get reconstructions which allow us to maybe synthesize in a controllable way new variants of what we've seen in the real world. And of course, I mean, this is an extremely challenging problem, right? Because in some sense, the complexity of the whole world is convolved into single pixel measurements. And of course, we are still very far from having reached this goal to be able to just reconstruct everything in the real world with just a snapshot of a camera. But I think we have taken some interesting steps in this direction, and I want to share some of these steps with you here in this presentation. So I want to start with some work we recently did on monocular reconstruction of digital human models. So we've been working on this for many years, reconstructing with, in particular recently, just single camera models of humans, entire bodies, faces, hands. So I'm going to start with a little overview of examples from recent work and then dive a little bit more deep in one specific problem in there. So one area here, which we've been working on for quite some time, is the area of markerless hand capture. What you see here is an approach that we are going to show now at SIGGRAPH Asia in a couple of days, which is one of the first methods that allows us to do from a single color camera in real-time reconstruction of both hands interacting, also under difficult occlusions from the camera, as you can see here. And it gives you the global pose, also like the relative depth, essentially up to scale of the hands with respect to each other. And this works in real time. And essentially what's behind here is a combination of a model-based approach and a learning-based method, where the learning component infers essential components that you see visualized here, like correspondence maps to a model, relative and intra-hand depth components, which we then combine with a model-based approach to get very high quality reconstructions of the hand just from a single camera, also for difficult interactions. So this is one area where we do a lot of work in. The other area is essentially markerless pose estimation, or actually markerless motion capture, also from single cameras. So here's an example work which we've presented at SIGGRAPH this year. It's called XNACT. So again, a combination of a deep learning-based approach with a model-based fitting step, which allows us to capture from a single color camera in real time the full skeletal pose and joint angles of actors, multiple actors also under different difficult occlusions in the scene, right? And this gives you the global 3D depth, again up to scale, right? So it's not only the pose root relative, but it's actually the arrangement in the scene as well. And by the way, this is also something which we make available as an API for you to download if you want to play around with that. Another area which we've been working on for many years is also to not only look essentially at the kinematic or the skeleton reconstruction of the human or the hand, but also to try to, in addition, reconstruct the non-rigid deforming surface geometry, right? So, and one work in this domain was this one here, which we showed last year as a talk paper at ZGraph, was called LifeCap. And what you see here is a method that allows us to, again, by combination of a neural network-based pose estimator and an analysis by synthesis deformable mesh fitter, to reconstruct here the pose as well as the non-rigidly deforming surface geometry in the human from a single camera in real time. Now, but solving this problem in this particular way was certainly a step ahead, but it also has pros and cons, right? I mean, there are certain limits also in terms of what the performance is that you can achieve with that. And our question was, for instance, can we do similar things like we show here with essentially with also an analysis by synthesis step at the end? Can we do that entirely with a neural network? And this is something we've shown now at CVPR this year, and the approach here is called DeepCap. And I should also mention that this was the best student paper honorable mention, so it received the best student paper honorable mention award. So here you see the algorithm in action. So it can, from monocular video, reconstruct pose and surface, non-rigid surface deformation. And we do this with a neural network where we establish kind of a new weak supervision scheme in order to train. So essentially, what DeepCap does is it uses a combination of different neural networks. So it takes as input a segmented input image of the human, and then we have one branch of a network, which is a pose net, that essentially extracts the skeletal pose parameters from the image. And in parallel, we have another network, which is a DefNet, which reconstructs the non-rigidly deforming surface geometry of the human relative, so to say, to a canonical pose of the human. And when you combine the two, essentially you get what you see on the right? So you get essentially the correctly posed, non-rigidly deforming plus skeleton posed surface. Now, let me just very briefly show you how this DeepCap algorithm works underneath. So one challenge here is, of course, if you want to do such things entirely with a neural network, is the question is where can we get training data which give you, for the relevant pieces of information, the ground truth information, right? And that's very challenging, right? It's already challenging for the ground truth 3D skeleton pose, but it's even more challenging for the ground truth deforming 3D surface geometry, right? So this is why in this particular work, we looked at how we can phrase this a little differently with kind of a weaker supervision scheme that still allows us to train networks that can reconstruct both of these aspects, surface and pose, at high quality. And essentially what we do there is we use supervision based on multi-view 2D joint detections, which are easy to compute for input images, as well as only foreground silhouettes. So we don't need full mesh reconstructions of the human in order to train this network. So, and essentially in practice how this works, so we have a multi-camera studio here. And in this particular case, we recorded a person with like 14 cameras. And for each of these images from this camera set, or from this data set, we compute now the 2D key points as well as the foreground mask, simply by a chroma keying background subtraction, which is relatively easy to do. And these data are then used to essentially train these two core networks of the DeepCap algorithm. So the PoseNet essentially regresses like global rotation as well as the joint angles. But there is another component in the network which also allows us, if we have pose 2D key points in the image, also to get the global translation. And we train this network essentially by, on the one hand, like a prior loss, which kind of penalizes implausible skeleton poses, but also essentially a multi-view key point loss, which checks the alignment of the, so to say, the post-prediction with the reprojection into the images. So that's the skeleton part, so to say. And in parallel, we have a deformation network, which is responsible for capturing the non-rigid surface deformation. And here we have also regularization by means of an as rigid as possible loss, but the main supervision essentially comes from a combination of also a kind of a key point loss for the joints, as well as a foreground loss against the foreground mask, which is essentially measuring how well the reprojected mesh aligns with, so to say, the silhouette boundary of the person, which is in this case represented as a distance transform image. Right? So this is very briefly how this algorithm is set up. Now, and once the algorithm is trained, and this at the moment we do this in a specific way, we can then apply it to essentially single images and do reconstruction, right? And here you see a comparison of our approach on the right, also the reconstruction here from one camera, but also overlaid with other reference cameras, which shows that it not only gets very well the pose also in global space, but also very well the deformation. And this is a challenge which some other approaches, earlier approaches like LiveCap, they struggle a little bit more with, in particular, getting the exact global 3D depth, for instance, correctly, right? Which is what you see on the left-hand side. Here is another comparison. So, of course, our approach, this is with other approaches from the literature at the time, right? So there's, for instance, the PIFU approach, which essentially works on an implicit representation. And our representation, of course, gives you a mesh which is deforming over time. And so it gives you also space-time coherence over time, essentially, in this reconstruction. This then allows us, of course, also to basically show the full 3D fly around for a reconstruction like this, where the input is essentially what you see on the top left, right? I mean, just keep in mind, this is a reconstruction from a single camera view. Of course, you can do some effects with that as well, right? If you basically reconstruct here this video here, and then you have the underlying model that you capture, you can do some virtual texturing by rendering this Superman logo here on on the model. So here is a little comparison, which also shows that really the additional estimation of the deformation also makes a difference in terms of the quality. Because what you see on the left is how it would look like if you only essentially track the pose and only visualize the kind of skin surface, whereas on the right-hand side, you also see that the additional deformation that actually captures the deformation behavior much more naturally, and also captures, for instance, the swinging of the skirt in this particular example. And then here's another result, which shows essentially that the approach can also be used for sequences that, well, essentially were recorded with a moving camera. Okay. Yeah, so this was essentially work that is looking at the entire human model and the reconstruction of the entire human in the scene. I want to briefly now talk about a slightly different important setting or important part, so to say, of a digital human model, which is the human face, which is an area where actually Matthias and his team and me and my team have done a lot of work in the past. So I want to pick out one work in this area, which is already a little older, but I'm showing it because essentially the idea behind here is also going to be relevant for something that I show later. So what I show here is an approach which at the time, so this was a nice CV paper in 2017, was one of the first that showed a kind of a new kind of integration of a deep network with a, well, you should say, a differentiable computer graphics algorithm to do face reconstruction. So it allowed us to do from a single camera reconstruction of the full 3D face geometry, reflectance, illumination, and expression parameters in a very short time, like 4 milliseconds in a forward pass. And as I already indicated, what's behind here is, so to say, a new way of integrating a model-based with a deep learning-based approach. And it has the additional benefit that it can also be trained in a self-supervised way on unlabeled image data. Now, what's behind here is what we termed a model-based phase autoencoder. And essentially, what that means is it is an autoencoder, and it is similar to convolutional autoencoder has an encoder stage, which essentially takes, in our case, of course, face image, and encodes that into a reduced dimensionality latent vector. But in contrast to a standard convolutional autoencoder, our decoder is not a convolutional neural network. It's actually a differentiable computer graphics algorithm, so a differentiable renderer. And it has the additional benefit that this renderer expects as input exactly parameters of a parametric phase model, like a morphable phase model. And each of these parameters has an exactly defined meaning. Now, which has the added benefit that we can, so to say, enforce the latent code vector to have semantic meaning as well, which is not so easy to do for standard autoencoders. So this, just very briefly, this parametric phase model is, and many of you have seen this before, I guess, essentially like a roughly a 300 parameter model, which has individual subsets of parameters. For instance, we have variables that describe the phase geometry, like phase identity, which was learned from laser scans of people, like 200 laser scans. It has other dimensions that represent the expression space using a blend shape model. Right? Now, and as I said, right, so what comes out essentially at the end is now a rendered image of a phase. And what the differentiable phase renderer does, very briefly without me going into much detail, is essentially evaluating the rendering equation here for each pixel in the image. So how light falls into the scene and how it's reflected into the camera. Of course, now on the basis of our scene representation in our parametric phase model. And this is differentiable and can be trained end to end. So we can phrase a loss at the end, which basically says, essentially what comes out at the end of this network should look like the input image. And this means we can conveniently also train this in a self-supervised way, right? We can essentially pick, image databases on the internet and use all of them jointly to train this type of algorithm. And now, of course, this is how the network looks at training, right? At test time, you don't need the differential renderer in that sense anymore. But what we do there essentially is we are only using the encoder part to essentially project into that latent space, which is the space of our parametric phase model. And what that allows us to do is essentially, once trained, forward pass is extremely fast. We can, from a single image, very quickly reconstruct the full model, including geometry, reflectance, and illumination. Right? Now, this is, so to say, a little bit of an earlier stage of the project. So this was essentially one paper in kind of a line of papers that followed up, and where we looked at further improving this type of approach. For instance, here in this work, we still used kind of a, you could say, a predefined phase model, right? Where the dimensions, so to say, of the identity space, for instance, were defined by what we scanned, essentially, or what was scanned in that database that was used here. The question for us was, can we, in addition to learning the reconstruction, can we also learn the model itself, like the phase model or the dimensions of this model? And this is something we did in one of the follow-up works to this work, which was a paper at CVPR in 2019. It was called Phase Model Learning from Video, where we actually, in addition to learning this reconstruction method, we also learned the dimensions, so to say, of the identity and albedo model, which allows us, as you can see in this video here, again, reconstruct these phases very fast, but at the same time also get better reconstruction quality out. Because now we are essentially expanding, so to say, the representational power of the phase model, also from in the wild videos. In this case, videos actually. So we used video data signal for that. Okay. Now, what is interesting is that in many of the works that I've shown, there was kind of a component which was looking at how can we combine so to say, established concepts or model-based concepts or expert-designed representations, so to say, in graphics and vision, with learned representation or deep learned representations, right? I think this was something which is a kind of a trade that is in all the methods that I've shown so far. And the question is, of course, can this concept of such an integration between learning-based and model-based approaches also be used for synthesis, for better synthesis of imagery, not only for the reconstruction part? And well, this is a rhetorical question in that sense, because yeah, the answer to this is yes. And kind of there is this new field of emerging, which we term neural rendering, which is essentially doing exactly that, and which is an area which we also had the pleasure and honor to do some contribution to. So as I said, right, I mean, neural rendering is essentially a new paradigm for image synthesis, right? And here are two examples from our work, so it allows us, for instance, to do kind of computer animation style control of videos of humans. Or it allows us, as in this work here, to even do something like a bullet time free viewpoint fly around from an input, just a single video of the person moving, which is things that would be very hard with standard animation or video editing packages. We've also shown that this was a work that we showed at SIGGRAPH together with our friends from Stanford, that you can, for instance, if you have a talking head video or portrait video like this one here, we have a textual transcript of what the person says. You can actually develop an algorithm which allows you to change that transcript at least in a small way, and then resynthesize. So these are only two examples showing that essentially this combination of established model-based concepts and neural network-based concepts essentially allow you to go in many ways beyond what classical computer animation packages or computer vision or video editing tools would allow you to do. So what I want to first show you, speaking of some recent work we did in this area, is a work which we are actually going to present also at SIGGRAPH Asia in a couple of days. And this is work we did together with our friends at Google. And it is called Deep Relightable Textures. And essentially what we're looking at here is a combination of volumetric multi-camera performance capture with a neural rendering approach. And what it allows you to do is that you can simultaneously synthesize the appearance of the person under multiple dimensions, like for instance, under a new illumination condition, or under a new viewpoint, or in motion, and essentially also using combinations of these dimensions that I just mentioned, like changing view as well as changing viewpoint. Sorry, changing lighting as well as changing viewpoint. Okay, so what's behind here is essentially, as I said, a neural rendering approach. So there's a learning-based component, and the data for this learning-based component is coming from a light stage setup. So a light stage is something that maybe many of you know, is a big dome of lights, but also with cameras equipped here. And in this case, it's 58 color cameras. And this dome of light has like around 300 RGB light sources, which you can, flash individually at a very high frequency, which would give you images from the cameras that are called one light at a time images, right? So what we do in this is essentially we have actors in a static neutral pose, and we take like 300 of these one light at a time images, but also two color gradient images, right? Which is kind of color gradients. When you sum them up, it's essentially the full light on, right? And for each of the camera views. And in addition, we also compute alpha masks from each of these views. And then we want to have essentially a generative model that can synthesize images of the subject under these dimensions, right? New viewpoint, new lighting, new pose, right? And this can also be done, as I will show later briefly, also for dynamic scenes, because essentially the goal is that we can, so to say, create this only from two gradient illumination settings, which is essentially only two lighting conditions, which you can also do essentially while you're recording video. And also the model should be trained in such a way that it can generalize to other individuals, which we essentially achieve here. And this is also done because we have essentially a training set which does not only show one subject, but it was actually around 80 subjects that were captured in this setup. Okay, so as the title already suggests, right? So there's probably some texture representation, and so this is very briefly the overview of the approach. So essentially, we have a neural network here, and it takes as input these color gradient images from all the cameras that are in the setup, and also some kind of pixel space encoding of the viewing direction. And first, what is done here is essentially there are feature maps extracted from these input images. And then they are actually, because this is now the model-based component, there is also a geometry model reconstructed for the person in the scene using like a photoparametric reconstruction approach with the cameras and the setup, which allows us to compute texture maps, right? So we can essentially transfer these features to texture space and actually aggregate them. So I have a pooling, which is here is actually a geometric operation. So it's like a view-dependent texture mapping type combination of these features. And these combined or pooled features are then essentially convolved once more to create a final feature map representation or feature texture map representation, which is supposed to encode like the material and kind of local shape properties on the surface. And because we have this dummy geometry, or because we have this geometry model of the person, we can then essentially also warp these feature maps essentially into each target image by using the UV map. And this is then essentially the input to a neural rendering stage, which takes this kind of warped feature map and essentially computes two things, like an alpha mask for this target view, but also taking additional information from the geometry proxy, like a light visibility map or a reflectance map, which is then essentially fed in also to the last neural rendering stage to create then the final image of the person. And with this approach, we can, as I showed already initially, then sample these dimensions, right? We can essentially create renderings from new viewpoint while keeping the pose static, or also under static viewpoint while changing the illumination condition. But it's actually also possible to apply this to dynamic scenes, right? Because we only need 2 color gradient illumination images as input to this network. And we are also not expecting that the UV map or that the space-time coherence over time, right? So the UV maps can actually change over time. This here is essentially showing all together, right? Viewpoint change, lighting change, and dynamic or like time evolvement of the sequence. Okay, so far I've essentially shown how we can use this neural rendering idea, combining learned representations with explicit graphics type representations to create high quality imagery, but requiring a relatively complicated or a relatively sophisticated setup in order to achieve such quality. And one question we also asked ourselves is, can such a combination of model-based and learning-based also be used to enable more controllability of pre-trained generative models? And what I mean here in particular is essentially, just a second. So what I mean is like, so we have state-of-the-art generative models like this one here, which is the well-known style GAN approach, which allows you to essentially sample highly realistic images of faces, right? So the quality of these images is great. The disadvantage is it's not very easy to control in a semantic way the output of these models, right? Now, on the other hand, as shown also before, if we have a 3D morphable face model, we have a full 3D face, right? And we have very sophisticated or very detailed control over individual aspects of the model. But at the same time, most of these head models or parametric face model only represent the interior of the face. And it's also fair to say that what they represent is a good approximation of these faces, but it's not going up really to the level of full photorealism. So what we did in this work here, which is called Style Rig, is essentially we developed a generative model of such portrait images, which should preserve the synthesis quality of style GAN, but allow controllability similar to a 3D morphable face model. And essentially this is done by a learned mapping between these pre-trained or pre-existing models, like between an existing morphable phase model and an existing style GAN. So we don't need to create additional hard to collect like label training data for this. Okay, so most existing approaches for controllable image synthesis, like train separate conditional generative model for the given task. But training such networks is, in particular, if it's at high resolution, is often difficult, right? And in contrast, we essentially add controllability to a pre-trained model. Now, concurrent to our work that I present here is also other approaches that explore different kinds of adding such controllability to a pre-trained generator. But I think this is the first one, which I'm going to show here, which uses essentially a full 3D morphable phase model to allow that controllability. Okay, so let's briefly look at what is behind this style rig algorithm. So the input to the algorithm is a style GAN code vector, which is like also the input to the pre-trained style GAN network. And in addition, control parameters like target control parameters of this parametric phase model, like for instance, the head orientation that we would like to see in the output. Now we have this network here, which is called RigNet, that takes essentially these two types of input and so to say synthesizes a new code vector that corresponds to these desired target phase parameters. And in this work, we trained like separate networks for pose and expression and illumination. And here I will show how this works for the pose case, essentially. So we essentially aim to enforce two properties in the output. The first is that the phases in the output should be in the desired target pose in this case. And additionally, we also want that the other properties, that like the identity of the person or the expression and illumination, should be the same as in the original image. And in order to enforce this, we essentially use a differentiable phase reconstruction network that we introduce here, which is trained to estimate these properties, like for instance, phase properties, from a style GAN embedding directly, right? And for training that, we actually use essentially components of this differentiable rendering layer, which I've also shown before for phase reconstruction. Then we can enforce essentially an editing loss, which minimizes the target, the difference between the target and the predicted pose parameters. And for all the other parameters, we can have a consistency loss that minimizes the difference between the source and the output parameters. Now, but we are not phrasing that difference in like model parameter space. We're actually doing these differences in image space. And here again, we are using the capability of being able to synthesize images for these predicted parameters using a differentiable rendering layer. So also here, for the development of this, such integration of a model-based approach plays a role. Now, let us look at some results. So what you see here is the output of the approach on the right, and on the left is a visualization essentially of the input parameters of the phase model that we want to enforce in the output. And we can, for instance, synthesize very nicely out of plane pose edits here. Now this is changing another dimension, so this is now changing the phase expressions in the output. Right, and this also produces results of high quality. And by the way, all these results were actually synthesized per image, right? So this is not like a video-based approach in any form. Okay, and here we can also change the illumination. And please note, I mean, so the phase mesh is essentially incomplete, right? It's only the interior of the phase, but still the illumination editing output seem consistent on the entire image. Now, what we've shown here in StyleRig is essentially how to create, so to say, a better controllable output of a pre-trained generator. What we cannot do in this approach, or what we haven't shown in this work here, is how we could essentially use this to make modifications to an actual, like a real image that is given, right? For that, you need an embedding. And this is something we looked at in follow-up work. So this is actually also a paper that is now going to be presented at SIGGRAPH Asia, which essentially allows us to project a real image into this modifiable space and then do similar high-quality modifications on these images. So here also for face expression. What you see in the middle is essentially, so to say, the projection of the image, the input image on the left, into the space of this editable model. Okay, so maybe the last part here of my presentation is to think about how such neural representations or neural rendering approaches, which I've shown before, which are most of the work I've showed so far was on humans and human models, can be used maybe for a slightly broader class of scenes. And the approach I want to talk to you about is called neural sparse voxel fields. It's something that we're actually going to be presenting at NeurIPS. And what you see here is the output of this method. It allows us to do essentially free viewpoint rendering of scenes like this one here from inputs which essentially multi-view images of the scene. And you see the quality is quite good. And we can also essentially represent not only the shape nicely, but also view-dependent appearance effects in there. So what is the general idea, so to say, of using neural rendering or neural scene representations for free viewpoint rendering? Well, typically you have two components there, right? You have a scene representation that you learn, which you can think of as a learned mapping of like a spatial location, like a location in 3D space, to either explicit or implicit appearance or geometry information of the scene. And once you have that learned representation, you also need a renderer, which is able to synthesize normal views of this. And here, typically, one resorts to computer graphics style algorithms like ray-based rendering algorithms that essentially sample this scene representation in order to create the image. Now, there is a body of related work on this. I mean, this is by no means complete, but I just try to explain some kind of categories of methods here, right? So there are some methods which try to essentially learn something like vectorized representations of scenes, and then from that, using a neural network, creating new viewpoints like the generative query network. There are other methods which combine something like simpler shape proxies, like multi-plane images, also with a neural network-based representation to represent the scene and create new views. And then there are other methods like RenderNet here, or the deep voxels and neural volumes, which actually resort to something like an explicit discretization of the space on a voxel basis, and then learning essentially features or explicit appearance properties of the scene on that. And then there are essentially these implicit field type representations, which learn essentially a continuous function that can be sampled anywhere in space without necessarily assuming kind of an explicit or concrete discretization of the space. So our work is also related to this methods based on implicit fields. So as I already mentioned on the previous slide, here the goal is essentially to kind of learn a function typically represented with a neural network that represents the properties you're interested in space. So you can provide a location in space and essentially feed that to your learning network, and out comes, so to say, local properties at that location, which can be either features representing the properties there, or maybe explicitly values of color or opacity or at that space. And then essentially you can create an image of such a representation by using, for instance, a ray-based computer graphics style algorithm where you shoot rays through the camera pixels and sample this representation along the ray in order to accumulate and finally compute a color value into the image. Now, in order to create this rendering in the end, there are kind of two classes of methods which were used in the past for this. On the one hand, you can do, for instance, surface rendering, which essentially means when you're shooting a ray or you're sampling the ray, you're trying to find essentially where the surface lies. and then assign a color, so to say, to that particular point on the surface, which is, for instance, something that scene representation networks do. They're using like a kind of a trained ray marcher. And this is something that is computationally relatively efficient, also has some disadvantages. Sometimes it may lead to a little bit more blurry results because it may not be so easy to actually find these intersections. And then there are other approaches which actually do more classical volume rendering, in a sense, shooting rays through the scene and essentially computing a lot of samples along the way, which is computationally, of course, a little bit more expensive, but then maybe it has some benefits in terms of the rendering quality at the end. Now, in order to achieve a quality level like this, so it makes sense to basically have something like a volume rendering approach. But the question is, is there a way of also making that a little faster, right? And here, of course, you could also think about borrowing ideas from computer graphics and rendering literature in particular, which has looked into the question of how to partition space such that essentially you don't need to sample everywhere in space, but only there where relevant informations of the scene are. And that's why we have, for instance, in graphics, these hierarchical space partitioning structures like bounding volume hierarchies or sparse voxel octaves, which help you extremely in that respect. Now, and essentially with all these considerations, we basically thought about a new formulation of this implicit field-based representation and rendering, which we call neural sparse voxel fields. And the core idea is essentially to have a hybrid representation, which combines such a kind of voxel-based space partitioning representation. This is the sparse voxel field, so to say, with a voxel-bounded implicit field representation. So we learn, so to say, within these voxels, implicit field representations that are constrained in there in a sense. And what that means is we get both a quality improvement because we can use the capacity better to actually represent the scene detail instead of doing it globally everywhere in space. But we also can render faster because we essentially can use the space partitioning structure to also essentially only sample on the ray within these voxels which contain relevant information. And as I already said, right, so we have, so this combines this explicit space partitioning, so to say, with an implicit field learned per voxel. And so what we do there is essentially we have a neural network, an MLP here, which takes as input like the ray direction, but kind of also in what we call a voxel embedding, which you can think of like a set of features that we are essentially storing at the voxel boundaries, which we then kind of interpolate to actually get the value at the sample location. But also we are using here, similar to earlier work, a kind of positional encoding of this voxel embedding representation to get higher quality also in the final output. And this can be essentially trained entirely from images. So both the voxel hierarchy, or the voxel representation or the voxel structure can be constructed from images, as well as these implicit fields per voxel that we need for representing the scene by essentially formulating a loss between the images that we see and the rendering of the scene. And essentially this is done in kind of a progressive learning stage where we're kind of alternating the improvement of these implicit fields that we learn with the further refinement of the space representation or the space embedding structure. Okay, and here are a few results of this. So on the left you see, so this is a synthetic scene completely learned from these rendered images of this scene, and you can see that with our approach, you get, compared to some earlier works, a much higher, much crisper reconstruction than rendering quality. This is another scene. This is a robot, also again reconstructed from images. You can see here that we also get a very good representation quality, very high detail in these 3 viewpoint renderings. Here are some more results from the NERF paper, which was a work preceding ours here in this space. So these are all synthetic scenes and now essentially reconstructed and re-rendered with our approach. But we didn't only test on such data, we also tested on some real data. So this is a relatively challenging scene from this blended MBS data set. You can see also here the spatial structure as well as the view-dependent effects are quite nicely captured in this learned representation. here is another comparison on this statue here from the same data set. And you can see also again, here we manage better to preserve the detail under these changing viewpoints. And here is also another effect which works nicely with our approach. Also the zoom in and zoom out effect actually works, which is not so trivial for many other representations in that class of methods. And I mean, this approach was not necessarily designed for this, but we did a little test also how this could be used for dynamic scenes, right? So here we essentially apply this to a multi-view captured dynamic scene. So this is reconstructed like with around 30 cameras. And here we are using kind of a hypernetwork approach to essentially encode the temporal involvement of these neural sparse voxel field over time for each of the frames. You can see also that works quite well. Okay, and the approach also lends itself for other computer graphics style edits that you may want to do quite nicely. For instance, you can also use, on the basis of that representation, actually more easily composite scenes with different elements to create it into a combined scene. All right, so with that, I slowly come to the end of my presentation. I mean, this is a very large space. There are also other works that we did in this area, which you might be interested in, and I encourage you to basically take a look at our group website. Maybe as a little advertisement for this, so we actually recently wrote a survey article on this topic of neural rendering together also essentially with many friends and collaborators here in that space. Also Matthias and his team contributed to that, and I encourage you to take a look at this. And with that, I'm at the end of my presentation. I thank you very much for your interest in our work. I thank my team. I thank a great group of collaborators that helped me many times to basically look into these problems. And I also want to thank some funding agencies that for some completely incomprehensible reasons actually give us money to do what we do. So with that, I thank you for your attention, and I'm happy to take your questions. Thank you.
Thanks a lot. Yeah, super impressive. I guess we have to update the state-of-the-art report because there's so much stuff happening right now. Yeah, are there any questions? I guess if somebody in Zoom has a question, just unmute yourself and ask your questions. And maybe I can start with a simple one. Yeah, I mean, one of the interesting things is always like this implicit versus explicit models, right? So also if you're comparing with like classic graphics algorithms, I mean, novel viewpoint synthesis, like image-based rendering is not necessarily a new idea, right? I mean, also you have done many works in these lines. So where do you think it's gonna go? Do we just, you know, get rid of these ones and we do everything with like implicit models now? Or do you think we have some combinations? What's your take on it?
Yeah, so no, I don't think that's actually going to happen. So I think what I found interesting here is that I think it's in particular, if you look at how you can make best use, so to say, of the strengths that these classical representations have, right? I think that helped us a lot of times actually to get, you know, a boost in quality, right? I think it's always interesting to think about, you know, where do, so to say, the learned elements, where do they contribute best, and what are the challenges for the classical methods, right? I mean, there are inaccuracies in geometry, you know, I mean, this is a never-ending story, right? And the question is it easier essentially in a learned representation to actually learn the compensation for that? And I think in the future we will see more of that, and that's, I think it has quite a bit of promise.
I mean, I have maybe a follow-up question. I mean, if you're thinking about the classic novel viewpoint synthesis methods, and let's say you keep images around, then the task is you want to kind of blend between the viewpoints, right? Mm-hmm. So in a sense, one question is, do we want to keep this information explicitly around in an image, or do we want to kind of put it into an implicit model? That's the high-level question, right?
Yeah, I mean, I don't think I could already fully conclusively sketch that space, right? I mean, you know, I think we as a community, and you and your team and me and my team, right, we looked into, you know, what part of the problem do we encode explicitly, as you said, on the geometry, or maybe even in feature space and so on, right? I'm not sure if it's already conclusively answered. I think there is some pros and cons depending on exactly what aspect we're talking about. I think we will probably see a little bit more evaluation of that, but I see a lot of exciting work now coming out, which is essentially, you know, sampling that space more systematically, right? We as a community do. So.
There's one question on YouTube. Why don't we use CNNs for the neural render? I assume it's for neural rendering. Why do we use MLPs actually for these models? Why not CNNs?
Well, the thing is, I think it's kind of a maybe a combination of a capacity versus representational power need problem as well, right? So I think it's also something that is maybe a slightly more compact thing to do in order to actually, in combination also with the space partitioning, to actually get good quality. I think this is also one of the questions always here in that case. And the other question is, you know, what do we convolve, right? I mean, so question is, what is the input to it, right? So.
Okay, are there any other questions on Zoom? There's a couple more on YouTube, but if anybody wants to ask a question here, feel free to speak up.
Hi, Matthias. One here. Can I ask a question?
Yeah, of course. Just go ahead.
Thanks for the talk, Christian. I have a question with the style rig. So in most of your work, it seems to be like you use a GAN. What do you think that in the future, like a GAN will be still the best choice, or there will be another, like a possibilities like a flow or variational autoencoders?
So a very good question. I mean, as you already said, right? I mean, there are very promising other types of representations, like also flow-based representations, which have been used for other problems, also in graphics, like for motion, for instance, right? Also VAEs. I think here for us the question was that, of course, I mean, we focused on the question because there are now many very well-trained such GAN-based models out there, right? I mean, can we attach, so to say, the controllability to this part? I think in that work the question was not necessarily trying to answer if that's the best generative model representation, but trying to interface with it, right? But I think, you know, the truth is, you know, maybe in the future we see more different variations of that, right? And which can also be maybe trained end to end again, right? With the model in combination with also flow-based representation. So I don't think it's crystal clear settled yet to me, right? I mean, I think there will be more exploration of other possibilities as well.
Any other questions here? There's a pretty good question on YouTube, actually. So what's your intuition in building the implicit models for neural rendering incrementally, right? Similar in the SLAM framework, right? You're getting more and more images. Like, can you build this up incrementally, possibly doing it in real time?
Well, I said good. No, I mean, it's a good question, yes. So, and I should say, maybe take a look at something that might come out in archive in a very short time, where we show something that goes a little bit in this direction. Let me put it this way. So I think there is possibilities to do that, yes.
Yeah, okay. Any other questions here? I think, Angie, you wanted to ask something.
Thanks for the talk, Christian. I have maybe a more high-level question. So in terms of maybe both the tracking stuff that you talked about, as well as all of this on neural rendering, how far do you think we can get without explicit modeling of physics, given that this is kind of the underlying basis for most of the stuff that you're trying to capture?
So I think it's a big omission, I should say, maybe for a lot of the work that we did in my team, but maybe for also other teams, that we haven't tried maybe to think a little bit more explicitly about physics-based representations. Actually, there's one work which I also have as part of my slide deck, which I didn't have time to talk about. So we're actually going to show a paper also at SIGGRAPH Asia, which is called PhysCap. And what we do there is we are improving actually pose estimation, monocular pose estimation, by using an explicit physics-based representation as part of the reconstruction. And so I definitely believe that in particular, if we move to this regime of trying to learn such representations more or less entirely from unlabeled data in the wild, you should be using such stronger knowledge about the interaction in the reality that helps you to better constrain the problem. So I definitely think we will see probably more of this in the future. So.
Any other questions? There's another one on YouTube, which is, it's similar to the first one. It's basically, can you do like scene editing? Like what's your take on basically doing scene editing with neural representations? Like how do the updates work and so on?
Yeah, I mean, it depends a little bit on what type of quality or what type of effect you would like to preserve, in a sense, right? I mean, if you're talking about, you know, being able to represent everything like interreflections and whatever higher order lighting effects, of course, I think there's a lot of this is still a little bit unknown, right? How we represent that, but it's still also interesting questions of how to infuse that into these neural representations. To think about, let's say you have, or even the question, you know, if you have a neural representation with a classical CGA model, right? I mean, how do you combine the two, right? I think these are very interesting questions that probably we as a community are going to look at in the future. But I think it's doable, right? But I think it needs a little bit more consideration.
Cool. All right. I think we're slowly coming to an end. Really, thanks a lot for the fantastic talk. I mean, obviously, it goes without saying, like for everybody who's watching, we can clearly see that your group is doing really fantastic work, driving the field forward. And the speed, generally speaking, of that community is just impressive, right? I mean, it's phenomenal. We can do really cool stuff now. It's really nice to follow all of these lines of work, and really great job also from your team. Yeah, so thanks a lot.
Thank you, and thanks to everyone for listening in, and thanks for having me. So
we will then move to the private part of the questions, but otherwise, yeah, thanks so much for having you.
All right.
Okay.
Thanks a lot. Bye everyone.
Ended the stream.